Hello, this is Andy from the Engineers Academy, and in this video we're going to be simulating the behaviour of a diode. And in particular we're going to be producing a VI or voltage current characteristic curve for the diode. The software that we're going to be using is OrCAD, and underneath this video I'm going to provide instructions on how you can obtain this software free of charge. And I'm also going to provide a link to an earlier video where we used OrCAD to simulate RLC circuits. So once you open the OrCAD software, the first thing that we need to do is create a new project. And as we're simulating diodes, I'm going to call this project Diodes 1. You would also specify the location as to where you want that project to be saved. The other thing to ensure is that you select the option at the top for PSpice Analog or Mixed AD. And that's analog or mixed analog digital. The reason you need to select that option is because PSpice is the simulator that we're going to be using. And we're going to create a blank project, so we can select that option and select OK. So once OrCAD fully loads, we can begin designing our circuit. And the first thing we're going to do is place our components. So the first component that we're going to need is our diode. So in the menu at the top, you click on Place, PSpice component, once again because that's the simulator we're going to be using, and then select the diode. You can then left click anywhere on the page to place that diode. We'll place these components in the correct orientation in a moment. The next thing we're going to need is a resistor. So again, place, PSpice components, resistor, and we can place that on our page. We also need a supply, so place, PSpice components, source, and the type that we're going to be using this time is a voltage source. And we're going to be using a DC voltage for our diode. Okay, let's zoom in slightly. And the next thing that we're going to do is orientate our components. So if we click on the arrow for select, then we can select each of those components and place them in the right orientation. So starting with our diode, we click on the diode, right click, rotate, and we're going to start with the diode in forward bias, like so. Next we need to connect our components to create a full circuit, and we can either use the place wire icon in the right hand column, or we can use place wire from the menu at the top. And then it's simply a case of clicking on the boxes between each of the components, like so. Okay, we do need one more component before we can run any simulations, and that's a ground. Once again, we can select that in the menu on the right hand side here, or we can go place, ground from our menu at the top. And we're just going to leave all the settings as they are by default and click OK. And we're going to place our ground at the bottom of the circuit. Don't forget to connect the wire between the ground and the circuit, like so. So now we have everything in place to run our simulations. Now we could change the labels on each of these components. We have V1, R1 and D1, but at the moment that seems sensible to leave those as they are. And we also have a voltage supply of 0 volts. Now when we run our simulation, we're going to be doing a voltage sweep. So once again, we can leave that as it is. And for the purpose of this simulation, our resistor value is somewhat arbitrary. What we're trying to demonstrate is the behaviour of this diode as the voltage increases. But you could produce the voltage current characteristic curve for this diode with any resistor in this position. Okay, let's set up our simulation profile. So again, we're going to click on PSpice in the top menu, and we're going to create a new simulation profile. Let's call it Diode 1 for consistency. And create. And now we can set the options that we want for our simulation. The only menu on the left hand side that we're interested in is Analysis. And the type of sweep that we're going to do this time is a DC sweep. We've got a DC circuit, so we're doing a DC sweep. And the type of sweep here on the right hand side that we're going to be doing is a voltage sweep or a voltage source sweep. Now recall that the name of our supply voltage in this case was V1, and we need to make sure that that corresponds with what we place in this box here. We're going to do a linear sweep, and we need to specify a start and end voltage. We're going to start at 0 volts, and the important thing to remember about diodes is that they activate somewhere between 0.6 and 0.7 volts. And it's that activation voltage that we're keen to investigate. So I'm going to specify an end voltage of 1.5 volts, and I'm going to go up in 0.05 volt increments. And you can play around with this and see what yields the best results. We click apply, we click OK, and now we're ready to run our simulation. The way that we run our simulation is using the Run PSpice icon here, or in the PSpice menu, the Run icon here. Okay, so once the simulation has finished running, down at the bottom of the screen, we can see that PSpice has opened automatically. So if we click on that window, and we have the screen here, which already shows our voltage on the x-axis, and we see our voltage values ranging from 0 volts up to 1.6 volts. Now we only need to plot one thing on here. We need to plot the current that's flowing through the diode, because what we would expect is once we reach our activation voltage of 0.6 to 0.7 volts, we would expect to see a current to begin flowing through the diode. Up to that point, no current should flow. So in the menu at the top, I'm going to click on Trace, Add Trace. And there is a shortcut for this in the menu, although the icons on the screen here appear quite small. So Add Trace, and we want the current through the diode. And we see that that's actually the option at the top, I for current, open brackets D1, which was the label attached to our diode, close brackets. So if we click OK, now it's important to point out that what we're looking at here isn't the voltage current characteristic curve for the diode, because our bottom scale here is the supply voltage, not the voltage across the diode. But what this plot does show us is that the current flowing through the circuit and through the diode is 0 until the diode activates at around 0.6 volts. Once the diode activates, the current flowing through the circuit increases proportionally. Now the reason for this is because the diode voltage is capped at around 0.6 to 0.7 volts, meaning as the supply voltage increases, the current in the circuit's going to increase. And that's why we see the current increasing proportionally as the voltage continues to increase. The increase in voltage causes an increase in current, and there's only a certain amount of voltage that's dropped across the diode. If we want to produce the voltage current characteristic curve for the diode, then what we need to do is change this bottom axis to the voltage across the diode. So on our y-axis, we have the current through the diode, which just so happens to be the current through the circuit. But on our x-axis, at the moment we have the supply voltage, and we want to change that for the voltage across the diode. Now the way that we change that bottom axis is by going to the top of the screen, and on plot, we need to go to axis settings. Now it's the x-axis that we want to adjust, and down here we have a label that says axis variable. Now at the moment, the axis variable is voltage V1, or the supply voltage. But we want the voltage across the diode as a result of V1. So if we look down our list, here we have V1 open brackets D1. And that's going to be the voltage across the diode as a result of the supply voltage V1. So let's select that and click OK. And when we click OK here, that will change our x-axis. Okay, so now we can see that our x-axis is V1 D1, or the voltage across the diode as a result of the supply voltage. Now what we have on the screen here is the voltage current characteristic curve of the diode, because we have the voltage of the diode plotted against the current of the diode. And once again, what we would expect is once we reach the activation voltage, the voltage drop across the diode remains fairly constant, but the current will increase as the supply voltage increases. Now we can emphasize this point about the voltage drop across the diode, and the way that we can do this is by resetting our x-axis. So I want the x-axis to be the supply voltage. So I go to Plot, Axis Settings, Axis Variable, and I want to change that back to V1. And our original graph returns. Now this time, what I'm going to plot against the supply voltage is the voltage across the diode. So I'm going to remove this trace by clicking on the label and deleting. And I'm going to add a new trace, which is the voltage across the diode. So trace, add trace. We've already said that the voltage across the diode is V1, open brackets, D1, close brackets. And here we have a plot of the voltage across the diode. So what this shows is when the supply voltage is low, say 0.2 volts as an example, all of that 0.2 volts is dropped across the diode. 200 millivolts is just the same as 0.2 volts. And it isn't until we get to 0.6 volts that not all of that voltage is being dropped across the diode. It's at that point that current can flow because the remaining voltage is being dropped across the resistor. The same is true at 0.8 volts because the voltage dropped across the diode is 0.6 volts. Therefore, the voltage dropped across the resistor must be 0.2 volts. We have a potential divider set up there. Now, as the voltage dropped across the diode never exceeds 0.7 volts, increasing the supply voltage increases the voltage dropped across the resistor and therefore increases the current in the circuit. And that's exactly what we saw on the earlier trace. Okay, so we are going to look at one more plot, and this time what we're going to do is reverse bias our diode. So if we return to our circuit, and all I'm going to do is select my diode and rotate it through 180 degrees. Now all other parameters I'm going to leave exactly the same, so I'm just going to rerun the simulation. And now let's look at the current through our diode. So trace, add trace, current through our diode. Okay. And this time we see as the voltage increases, we get a very, very small current flowing through our diode. Now in the case of an ideal diode, what we would expect is absolutely no current flowing. So we would expect a flat line here. But it's important to note that the units on our y-axis here are in picoamps. That's times 10 to the minus 12 amps. So what we're talking about is tiny, tiny currents flowing through our diode. These are negligible in comparison to the currents that flow through the diode in forward bias. But the reason we get this very small current through the diode is because of something called leakage. And this current here is known as the leakage current. However, it's important to reinforce that if this was an ideal diode, then the current flowing would be zero in reverse bias, and we would see our VI characteristic curve in forward bias.